All right, let's look at number 1. We got a stuntman. He's going to try to make this jump from building 1 to building 2. They're 4 meters apart. Building 2 is 2.5 meters lower than the first building. All we're given is his horizontal velocity, initially at 5 meters per second, and the angle that he jumps at. He's going to jump 15 degrees above horizontal. Is he going to make it or not is the question. Well, we don't have enough information right here to know if he is or not. He's not going to be able to just go perfectly horizontal because gravity's going to pull him down. Gravity only acts so in the y-axis. So we have to break this into chunks, and we have to break this into components, the x component and the y component. So we need to find out his initial velocity in x and his initial velocity in y. We already know his initial velocity in x is going to be 5 meters per second. And since acceleration due to gravity only works in the y-axis, that's never going to change throughout this daredevil stunt. We need to solve this component right here, the y-axis. This is 5 meters per second. This is what we're looking for. The angle is 15 degrees. So we can use tangent here. We're looking for opposite. We already have adjacent. Tangent, 15, equals opposite, which is our unknown, the initial velocity in the y-axis, over 5 meters per second. If we multiply both sides by 5, that'll get the initial velocity in y by itself. And our initial velocity, 5 tangent 15, is going to be 1.34 meters per second. All right, with a question like this, we have to focus on the y-axis. The x-axis won't come in until later. It's important that we keep the y-axis material apart from the x-axis material. So in the y-axis, 5 meters per second never comes into play. And in the x-axis, gravity is non-existent. Y-axis goes directly with gravity. So we need to know how long does it take a person, regardless if he's moving horizontally at all, to jump straight in the air at 1.34 meters per second and come back down and land 2.5 meters below where they initially started. Well, we can't use this equation just yet because we would have two unknowns. We don't know the final velocity and we don't know the time. We'd be solving for two things. It's impossible. To start off, we must use this first equation and find out that final velocity in the y component when he jumps straight up at 1.34 meters per second and when he lands. He'll land 2.5 meters below where he started. What's his velocity at that instant? So Vf squared equals Vi squared plus 2a change in y. We're solving for Vf squared. We know the initial velocity, 1.34 squared plus 2. A is gravity, negative 9.81. And then change in y is y final minus y initial. Well, his y final is going to be negative 2.5. Since this is where we're starting our coordinate system, initial would just be 0. So negative 2.5 minus 0 is negative 2.5. If we plug that into a calculator, we get that Vf squared equals 50.84. Let's get Vf squared by itself. And the final velocity in the y-axis equals negative, because now he started traveling up, now he's traveling down towards the ground, negative 7.13 meters per second. All right, now we know the initial and final velocities in the y-axis. Now we can solve for time. We'll use this equation and find out in the y-axis alone, when he jumps straight up at 1.34 meters per second, and he comes back down 2.5 meters and lands at negative 7.13 meters per second, how long it takes. So Vf equals Vi plus At. And remember, this is in the y-axis. We're using these two components. Negative 7.13 equals 1.34 minus 9.81, which is gravity, time. We subtract this over here, cancel that out. We get negative 8.4, there we go. 8.47 equals negative 9.81 t. Divide gravity out here to get t by itself. And we know now that the time this whole trip takes is 0.86 seconds. All right, when we're working projectile motion problems, the only thing that's consistent between the x-axis and the y-axis is time. Starting off, we solved for the y-axis final velocity. Then we found the time in the y-axis it took to go up at this velocity land at this velocity, which was 0.86 seconds. Now we can transfer our time we solved for to the x-axis. So this is where we seal the deal. In the x-axis, since velocity is never changing, there's no acceleration. It stays at 5 meters per second the whole time. We can use this equation. xf equals xi plus vt, because velocity is constant. Xi, the initial x position is 0, that's where we started our coordinate grid, plus our velocity, which is 5, and then multiplied by time. And we get the final distance in the x component is equal to 4.3 meters. So yes, he lands at 4.3 meters from this spot, so he's going to make it and have a little bit of room to spare. Number 3 is another projectile motion problem. It's always a good idea with these projectile motion problems to draw out a nice diagram so you can kind of visually see what you're trying to solve for. We have a salmon who's swimming upstream. He's 2 meters away from a waterfall which is 0.55 meters high. What the question's asking us is, if that fish leaves the water at an angle of 32 degrees above horizontal, what's the minimum initial velocity he needs to leave the water with in order to make it up to that waterfall and keep on his way? Well, we need to use the y-axis to solve this problem. We know if this fish jumps straight up into the air, regardless of any horizontal motion at all, he jumps straight up into the air, and the y component at its highest point, right before he goes from having positive velocity to back down negative velocity, that highest peak at 0.55, if that's how high we're jumping, we're going to have a velocity of 0. So let's use that to our advantage. Let's use this equation, and let's use a height of 0.55, that highest peak we're trying to reach right now. His final velocity would be 0. Vi is what we're solving for. A is gravity. Change in y is y final minus y initial. And since his final is 0.55, his initial is 0. That would just be 0.55 positive. Plug that into the calculator. We get 0 equals Vi squared minus 10.79. We'll get 10.79 on the other side. Vi squared equals 10.79. Square root of both. The minimum initial velocity in the y-axis. So velocity initial y has to be 3.28 meters per second. All right, so we know in order for this fish to make it to the top of this waterfall, he needs to have a y velocity of 3.28 meters per second. We know that he's leaving at an angle of 32 degrees. So now we just need to use some trigonometry to solve for what the initial velocity out of the water needs to be. We have the opposite side. We're looking for the hypotenuse. So we'll use the sine equation. Sine of 32 equals opposite, which is what we have, 3.28, over our hypotenuse, which is the initial velocity right out of the water. Multiply both sides by Vi. Then we'll have get sine of 32 the other side. And we'll end up with Vi is equal to 3.28 divided by a sine of 32. And the minimum velocity our fish needs to leave the water with in order to make it up that waterfall safely is 6.19 meters per second.